Good afternoon, everyone. Welcome and thank you for coming. My name is Michael Kölling and I will talk to you today about Greenfoot. I assume you know that because you're here, so you have looked in the program. In some sense, this talk is a bit of an odd one out at Devoxx, where we have a mostly technical crowd, and this talk is not actually very technical. It is a lot about teaching. It is about tool development and it is about Java, but it is about Java in another sense than many of the other talks. What I will talk about is how you can get kids interested in writing code. In a crowd like this, for me it's a bit of an unusual crowd to talk to. I talk much more often to teachers than to technical people, but at least today then I don't have to explain the Java so much as I usually do. I can go a bit quicker over those. We find that just in the last year or so, many times people who write code as their day job are getting interested in going into schools and running computer clubs or supporting their local teachers. And I assume, since you're here, that you may be in a similar situation, so I don't really have to tell you much about this. So I will today do a lot of demo, and I just want to show you one tool that's called Greenfoot that you can use to get young people from the age of about 14 or so started with writing code. I have here on my first slide, I don't like bullet point slides, this is my concession to the Devoxx slide deck template that they sent me, where I filled in the About Myself slide, and you see I work at the University of Kent, and Greenfoot is one of my projects that I work on. Now, this slide is a reminder for me to just show you my first demo, so I will try to keep the slides a bit to a minimum and spend most of my time here doing demo and just show you what Greenfoot looks like and what you can do with it. I think that's the best way for you to get an impression what it is. So I will go here to my demo. What you see on screen here, this is the Greenfoot environment. So I have Greenfoot open here already, and I have a project open. In Greenfoot we call them scenarios, so I have a scenario open. And it is a Java program. So here on the right, what we see here is a class diagram that shows me the classes that are involved in this project. What we see here in the main part of the screen is what we call the world. This is where things will be happening. And this is a project where I already have some classes written. You can see here there's a thing called Wombat. A wombat is, many of you will know that, some kind of round, brown Australian animal. Actually, I moved to Australia once, and before I moved there, I'd heard about a wombat, and I've never seen one. And I had an Australian colleague, and I asked him, what does a wombat look like? And he said, a wombat looks like, and then there was this long pause, and then he said, a wombat is an animal without any distinguishing features. So if I have a class here in my diagram, I can just click on it, and I can interactively instantiate the class. So what I'm doing here now is actually interactively creating an object of the class. And if I create an object, I can drag it into my world, and there's my object. And when I have an object in my world, I can click on the object, and there I can see all the public methods that this object offers, and I can interactively invoke those methods. So here, for example, is the move method, and if I invoke move, that wombat moves forward. And we can look at that again. I say move, and it moves forward. I can also see what else it's got. There's a turn left, and I can tell it to turn left. I can, of course, also, if I have a class, as you all know, create multiple instances, and for you that might seem obvious and normal. In a teaching context, that is actually a very important thing to do. The relationship between a class and an object is actually pedagogically, it's a very hard concept to grasp for beginners, especially in traditional environments. If you think of coding in Eclipse or NetBeans, if all you ever see on screen is lines of code, what you think of is lines of code. And the distinction between a class and an object is actually a very, very hard concept, and a lot of people are struggling with it. It's very hard to explain. In an environment like this, you don't actually have to talk about much. It becomes immediately clear that the classes are things over there that you use to generate objects from, and the objects are over here, and you can talk to them, and you talk to them by invoking their methods. So far, these were all methods without parameters, and I can also invoke methods that have parameters. For example, here's one that's called setDirection, that has an int parameter, and if I invoke that, if the method expects a parameter, then I just get a dialog box that prompts me to enter a value, and if I enter the value and click OK, then that method executes. I can do the same with methods with return types. So here is, for example, a canMove method. That's a Boolean method that just asks this wombat, can you move forward right now? And if I invoke that, it answers with true. And then if I take that wombat and drag it over here so that it faces the edge of the world where it can't move forward, and I ask it again, can you move now? Then it says false. So here you can do that actually to experiment very easily and quickly with the methods and the return values, and you can get the kids to play with this and play with the method invocation and play with parameters and return types and get a feel for what it is and how they behave. You can also inspect this. If you inspect an object, you're essentially opening it up and you're looking inside and see all the fields in the method. And there we can see this wombat stores its direction, how many leaves it has currently eaten. And of course, because I haven't created any leaves, that is 0. It has its x and y coordinate and so on. And we can actually see this in action. So for example, the origin, of course, is the top left, so here's a 0, 0. So the x and y 5, 2 coordinates, that is this wombat here. And if we watch the y coordinate, which is currently 2, I can just leave that open and now tell this wombat to move, and we see that this has changed to 3. So another interesting thing we can do is actually inspect 2 of them and compare them, and then you see, they have exactly the same fields, the same names of the fields, the same types, but the values for the fields are different. And then you can actually explain and discuss that that is because the number and kind of fields is actually defined in the class, and they are of the same class, so they will always be the same. But the values are held in the object individually, and they get the sense of the state of an object. One thing that is a bit, well, first of all, let me create some leaves. And the world, of course, which is the background here, the world is an object as well. Here's the world class, so I can also invoke methods on the world. And I have here, for example, a method that just puts some leaves into the world. And we've got those as well. One method is a bit special. So I can, if I look at the wombat here, there's one method called act. And if I call act, the wombat will just do whatever it wants to do. The act method is special because it is built into the Greenfoot framework. So here, if we looked at the class diagram, the 2 superclasses here, world and actor, they are part of the Greenfoot environment. They will always be there. And the subclasses underneath, they are part of this particular scenario, so they will change with every project I have. But the act method that these actors have, so all the actor classes are the ones that can live in the world. Because the act method is obviously defined in the actor, it will always be there, and it's known to the environment. And down here is a button called act, and what this button does when I click it is it invokes the act method on every object in the world. So it's just like calling act on every single object. Now if I do that again, I see they all do something. And if I click run, run is just a loop around act. So if I click run, it just calls act repeatedly over and over, and my wombats are running around. And at the moment, actually, it looks like there's only 2 because there's 2 right on top of each other. But it is actually, I can adjust the speed. So, and that is how you execute programs in Greenfoot. So there is no main method. There is no public static void main. All you do is you implement act methods of your actor classes, and things take off from there. So this is the overview. Well, this is pretty much what we do in the first 20 minutes. The last thing I do there is then we open up the class and we look at this and we see there is all this mysterious text here. And if we look at that, we just say, well, this is Java code behind every class. There is a lot of Java code that determines what objects of this class can do, what the methods are, and so on. And then I tell them we will now spend the rest of the term to learn how to write this stuff. Spend the rest of the term to learn how to write this stuff. But then the important thing is, from then on, when they learn to code, they do it in the context of modifying or creating behavior for objects. So the first thing we discuss is not where do the curly brackets go, where do the semicolons go. We don't start with the low-level problems. We start with the big concepts of object orientation. The big concepts of object orientation, that is things like what's a class, what's an object, behavior, and state. You can discuss those in Greenfoot before you have to discuss the syntactic details. So there's a pedagogical pattern that's called early bird that says, if you want to teach something, if you teach a course, decide what is important to you, what you really want the students to remember, and those things teach them early and often. So we start with the things that really matter. young programmers, they always learn syntax at the end. That's actually not your problem. At the beginning, they think that's the problem. They think syntax is what's hard. We all know that is not actually what is hard. The big concepts is what matters. So we do that early and explicitly. That is not easy without specific tool support, and that is exactly what Greenfoot is trying to solve. For Greenfoot, there are two perspectives. There's a student perspective, and there's a teacher perspective. For the student perspective, Greenfoot is an environment to write games. For the teacher perspective, it's an environment to illustrate object-oriented concepts. Before I want to spend some time in a minute writing some code so that you get a feel for what it is actually like to code with Greenfoot. But before I do that, what I want to do is I just show you a few finished Greenfoot projects, just so that you get an impression of the scope and kind of projects you can create with Greenfoot. So if you have wombats running around, it is actually not very far from there to then also have a project like this. Keyboard now. Okay. I'm not very good at playing this. I try again. So you get the idea. It's the classic asteroids. And what this is trying to tell you is, the quality, the performance, well, I haven't actually implemented the scoring yet, so I always get 999 points. It's not too bad. What it's telling you is the quality of games or applications you can create with this is easily good enough to write real playable games. So that is reasonably easy. So getting two-dimensional animated graphics on screen is what Greenfoot is good at. Greenfoot makes that part easy, and everything else you can think of in that context you can do. It is, if you want to teach coding to kids, it is important not to bias it too much towards the boys. We all know we have a real, lack of females in our profession. There is this big void. We are not reaching half the population, and our teaching of programming is often actively turning them away. So it is, as if you go into a school or go into a group of kids and you want to teach them, it is important to be aware of, not to bias it too much to the boys. And these shoot-'em-up games, like the asteroid games, is in danger of doing that. There was a sort of myth going around for a few years in the computing teaching community saying that girls don't like computer games. If you want to attract girls, don't do games. And there are now several studies that show that's not true. That's actually complete rubbish. But girls like different kinds of computer games. And that actually has been shown very convincingly, where girls much more often play more constructive games and boys play more destructive games. I can see that with my daughters. They play Sims all day long. They actually do like games, but they don't play shooting games. There's also actually a thing about context. I do a lot of workshops with kids, where school kids come into me, and there is a clear difference in behavior between the boys and the girls, where girls much more want to see a purpose and a context for it. With boys, I can just tell them, make this blue thing shoot this red thing, and they do that all day long. And girls typically say, why? So it's good to have a kind of context and story. So this here is another example. Actually, that doesn't do very much. It's just a piano. And I can play it with my keyboard here. And that's all it does. But it's just to show you, that they don't have to be shooting games that you do. Of course, every key is an object. And the code, if you look at it, just looks like this. It just has 5 fields here. We remember whether the key is being pressed down at the moment. This is the key on my keyboard, on my laptop keyboard, that the piano key is listening to. So every piano key is bound to a laptop key. This is the sound that it's producing. And then it has 2 images. One is the key being shown up, and one is the same key being shown pressed down. And the constructor just initializes those fields. There's nothing there. And all the magic is these few lines of code that just says, if our key wasn't down before, but now on the keyboard, our keyboard key is being pressed, then we play our sound, show the image to be down now, and then remember that we are down now. And if we were down before and now the keyboard key has been released, then we show the other image again. And the play method actually is a one-liner because there's a play sound method built into Greenfoot. So the complexity of the code is easy enough to get to nice-looking examples fairly early on. And then you can, by just putting some nice graphics in, actually make some reasonably nice looking games as well. So here's one that is just sort of a marble game where you have to shoot the gray marble off the board using the golden marble here. And that's a reasonably nice looking game, only because that's actually nice graphics. The actual coding isn't so much more difficult than the asteroids thing. But that also shows you can connect the coding with other digital media activities. So often we do that as group works, and some kids work on the graphics, and some kids work on the sounds, and other kids work on the code, and then they all come together and do that in a group. And then they all come together and do that in a group. Okay, that's the kind of things we are getting at when we are working with Greenfoot. Greenfoot, the whole environment has just these 6 classes. It's a very small system. There are 6 classes. That's the whole API to the environment. And kids can learn that reasonably easy. After a couple of months, they know everything that is there. Actors in Greenfoot have 3 bits of state that are automatically visualized. They always have an image, they have a location, and they have a rotation. And you program graphical animation in Greenfoot just by changing the state. So just by changing the x-coordinate, a simple change of a field, you create animation that becomes immediately visible on screen. So you get essentially the graphics for free. So the code is all very clean. You just program state changes, and the framework will animate it for you. This is my reminder to actually show you a bit of code. So here, I've got another project. This time it's not a wombat, this time it's a turtle. I'm creating a turtle object, I'm putting it in, I'm clicking run, and nothing happens. And then we can investigate why nothing happens. We can open the editor, and we see here there is an act method there, but it's empty. So when this program was running just now, the turtle this act method was actually executed, so the turtle did over and over nothing. And now we can start writing some code by just putting in a method call. So there's, for example, a move method, and I can say how many steps I want to move forward. And if I put in move, I close this, I compile, and put my turtle in again, and I click run. Now the turtle moves. And then I can make it turn instead of move. If I make it turn, and I compile it and try that out now, it turns. And then, of course, you can get into sequence and do a move and turn. And then, of course, what happens? You should all know that, of course. It runs in a circle. The next thing we typically do then is to introduce if statements. One nice thing, actually, that I often do in class, and I think this room may be too big to do this, but I thought I'll give it a try anyway, is there is a, spelling error. There's a get mic level method that gives me just the noise level from the microphone. So if I say the noise level here in the room is more than something, so essentially what they're saying is, if there's some noise, then I want to move. That is one possibility to introduce an if statement. And now the idea is that you make some noise and you can see whether you can move the turtle. Because this room is very big and you're quite far away and it's actually going through my little laptop microphone here, I'm not sure whether you can actually be loud enough, but we will give it a try. I will run it and I'll give you a signal, and then I want you to make as much noise as you can. Now. Stop. Okay, we do that again, but this time you stop in the middle of the screen. Okay, so that was good. Actually, it worked a lot better than I thought it would. Go. Stop. Go. Okay, so this is the kind of thing, how we start in a class to play with an if statement. So the idea here is to have much more interactive, engaging examples of introducing bits of code and examples what you can do with this. And then, of course, if you don't have a whole classroom sitting there for you, and if you want to do things for yourself, then you do something like if there's an isKeyDown method where I can say left is the name of the left arrow key. So with an isKeyDown, I can just check whether any of my keyboard keys is being pressed. And of course, the character keys, the name of the character keys is the character. So the name of the A key is the A and B key is the B. And then the function keys have names. So left is my left arrow key. And I can say, for example, I want to move in any case. But if the left key is being pressed, then I want to turn a little bit to the left, and then I can copy and paste this and say, do the same for the right key. If the right arrow key is being pressed, then I turn 5 degrees that way. And if I try that out, I can run this, and now with my keys on my keyboard, I can control my turtle. So we get there, probably 15 minutes into the first session, we have a keyboard-controlled animated character on screen. And it's not a great deal of code, and it's exactly 2 concepts that you need for that. You need a method call and an if statement. So we get reasonably interesting looking effects fairly quickly. That is the goal with the motivation in Greenfoot. I actually had a script somewhere and I didn't get it out, so I hope I remember what I wanted to do next. The next thing we do then is typically give the turtle something to do. So we create a new class. I can create a new subclass here. When you create a class, of course, in Java, always your class gets a name, but in Greenfoot, a class also gets a picture. So here's an image library you can choose from. These images here are included in this project, and I've prepared an image for letters already. You can also, of course, here, using this button, use any graphic that you have anywhere in your file system, so you can create your own systems. You're not restricted to the ones coming out of the prepared library here. But if you have a new class, I can now put my letters in, and I can put my turtle in. And what I then want to do is I want to have the turtle eat the lettuce. And so then we get into other code that looks like this. If can see, so we are still in the turtle, and I say if, and there's the class being passed as a parameter. So if I can say if I can see an object of class lettuce, then eat, and eat also takes a class as a parameter. So it will try to eat any object of that class. And the way I have written my canSee method is so that the turtle is extremely short-sighted. It will see the letters only. It will see the letters only when it runs right on top of it. And now you see every time I compile, my objects disappear again. And that is, of course, necessary because the class that the objects were of now doesn't exist anymore because the class has been modified and the old one's gone. It is necessary technically, but it gets a bit tedious because now if I have more objects, I have to recreate them every time. So another thing I can do is I can click on the background and there's a save the world method. So I can save the world. What that does is actually it writes pure Java code. There's no magic behind it. It just generates some Java code in the turtle world class. So it generates code in this class, which is here in code, does exactly what I've just done manually. It creates the turtle and inserts it into the world at that location. And it creates lots of letters objects and adds it into the world. And that's put into a method called prepare. And the prepare method is called from the turtle world constructor. Because the one thing that automatically happens, and that's the only magic thing here, every time I successfully compile in Greenfoot, the one thing that happens automatically is that an object of the world class is being created. And that's what you see. That's what you see as the world. So the world class object is automatically created. And then by implication, everything that is written in the constructor of the world class is happening automatically. And so you can initialize the world, and that's what's going on here. And then if I now run this up, if I actually hit it, I can eat the lettuce. And then the next thing we do is we put a predator in so that the snakes eat the turtle, and that is actually very similar. We make the snake run around randomly, but then the code is actually very similar. They get just to practice the same thing over and over again, and you can play with random numbers a bit. But then we are very quickly at a game where you control the turtle, and you have to eat all the lettuce, and the snakes chase you, and you have to avoid the snakes. So within about an hour and a half, we are getting to have written the first computer game that you can really play. One thing that is actually quite good fun is to put some sound in. So what I can do is Greenfoot dot play sound, and I have prepared a sound file slurp.wave. And if I play this, that's really all it needs. the best way to generate this sound is actually to just record them. I have another version of this prepared. I don't want to write the snake now just to save a bit of time, but this is the same thing where it's already in there. And then if you want to now put a sound in where when the snake eats the turtle, for example, there is a sound recorder built in here, and I can just record a sound. So if I do something like I say, "Oh no," and then I can play that back, "Oh no." And the only edit operation you have is a trim, so I can trim off the silence at the front and back. So I trim that, I save that as "oh no," and save it and close. And then when the snake eats the thing I had, where is the, oh no, it's the other way around. The turtle checks whether it gets eaten somewhere, and there is a game over sound. Instead, I put "oh no" in there, my sound that I've just recorded, when the turtle meets the snake. And if we play that now, I avoided it this time. "Oh no." And so if you do this with kids, it's strangely effective to put sound in. Of course, putting sound in, programmatically, it's nothing. It's just another method call, right? So in terms of programming concepts, there was nothing new there. In terms of motivation, it's a huge bump. When I do that in classes, they are really running around, they jump out of their seats, and it is a really effective thing. And the other thing that is effective, if I just put my slide thing out here, are these things. What they all know is Gamepads. And so if you plug that in, and then you play that, "oh no." Oh, now we should start over. I can now control this. Oh, no, I didn't have that plugged in when I started this. I need to reopen this. Or maybe I need to restart Greenfoot, I don't know. I probably do. There is an API in Greenfoot for Gamepads, and if you do that, you can then control your turtle with your Gamepads. And so that is another thing that is actually programmatically well, educationally doesn't add very much, but in motivation it does. And then you can, of course, shoot tomatoes as well. So having these gadgets, having sound, having Gamepads, and that is all things that are really good fun. And what Greenfoot does for you is it makes it actually very easy to do these things and get them on screen. Do these things and get them on screen. I think I'll finish here with my turtle, and I move on a bit. Oh, I should, if I want my slides to go forward, I should plug this in again. I'll just tell you a few things about when you teach with these kinds of examples, what you should do and what you should think about. One thing is ownership. So if you can manage to get the kids to own the project they work on, it makes a huge difference. And own means, make their own decisions, think of their own stuff, and think of what they want to do. Of course, at the beginning, when you show them to write code, they can't write their own code because they don't know anything yet. But on the first day, right at the beginning, the things you can do with them is let them play with graphics and sound. So what I usually do, when I do the thing with my turtle eating my lettuce, the first thing before I do that, actually I tell them to just create another creature when I have my turtle. I get them, and you've seen that with the lettuce, that's really easy. That's, they can all do that in 2 minutes. So I get them to create their own creature, and when I make the turtle run around, they make their whatever else run around. And even though we all end up writing exactly the same code, they end up all with different stories. We can also very easily change the background picture of the world. And some change it to a space picture, and they have a rocket flying around collecting astronauts and avoiding asteroids. It's exactly the same code. It's the same program, just with different images, right? But they get really excited, and there is really, I have to admit, a gender difference. If you have girls, they often have fluffy bunnies running around eating pizza, and if you have boys, they have killer sheep eating babies. But the thing is, it's their idea, and suddenly they get really excited. And the story, actually just different images and the different ideas, a different story, gets them to different ideas what they want to do next. And that is taking ownership, and that gets them really, really excited. So we want them to get them as quickly as we can into a position where they can make their own decisions and take their own ideas into the program. That is very effective as a learning method. Use open problems. So when we teach them something, use a problem where they can actually go places. Now, when I learned programming, what we did in class at first is things like compute and print the prime numbers up to 100, right? It's a completely artificial problem, of course, because if I want to know the prime numbers up to 100, I would not write a Java program. I'm quicker with a calculator and a pen of paper. Or actually, if you really wanted to know the prime numbers up to 100, what do you do? Google, exactly. 3 seconds. That's what you do. You know, writing a program for it is completely artificial. Of course, there is some sense of satisfaction if you can do it and print out the numbers correctly. For a moment, you have a sense of satisfaction because you've proven to yourself that you can do it, and that's good. But as soon as you've run it once, there is no reason in the world to run it again. You know, why would you? The only thing you can do with it is throw it away. You know, it has no use. No one would ever do it in real life. And, you know, if you have a whole group of kids, some will need an hour to do that, and some finish in 5 minutes. The ones who had done it in 5 minutes, there's nothing else they can do. What, print them out up to 200 maybe. That's exciting then. So use a problem where they can make up new challenges and do more, you know, and just go further. And they come to ask you and say, how do I do this? You know, that's why games are so good, because they always have an idea what they want to do next. Project of discovery. So use a project. I've just told you about the prime numbers. You know, the prime numbers thing is a prime example, prime number example of a very close project where you find out nothing, you learn nothing. You are done when your program does exactly what you always knew already it would be doing. You know, there's no surprise at the end. You don't discover anything new. So here, I'll show you another example of the kind of thing we do. I have here a simulation. Actually, simulations is the other class of programs that Greenfoot is really very, very good for. Here I've got an ant simulation, and I've got 2 ant hills, and now you can program the behavior of the ants or investigate it or play with it. And the behavior of the ants is actually very, very simple. If you look at them, they run around entirely randomly at first until they run into some food. If they find some food, they pick some up and run back to the anthill, and they leave drops of pheromones on the ground. If they run around randomly and smell some pheromones, they just turn away from the anthill and go that way. And that's the complete behavior. Now, the interesting thing is if you get a single ant, like up the left there, finding the food, going back, it will not make its way back because the pheromones evaporate too quickly before it gets back. But if you get enough ants together, you get these stable trails forming. And that's fascinating because it's true emergent behavior. There is nothing in the code at all about path forming. No single ant knows anything about paths. And that is really fascinating. You know, this is something you really want to play with. When I wrote this, I was sitting there all afternoon playing around with this because that is actually good fun. And then you can start asking questions. You can say, well, what if we now introduce pollution into the environment, which has the effect that the ants smell only half as effectively as they did before. So they have to be half the distance to the pheromone before they can smell it. Question, will they still be able to form paths or not? Well, it's actually very hard to answer abstractly, but it's easy to try out. So you go and code. You change your code, you try it out. And that is because simulations is an area where computers are actually used. That's what computers are good at, and that's an area where you actually need a computer to run them. And so finding projects where it makes sense to use a computer, that is where it all comes alive. I can, by the way, also create objects interactively and drop them into a running program and have them interact with them as well. So it is fairly flexible, interactive, experimental. You can experiment a lot, and you can find out things and learn that way. The next tip, use real data. And actually, I am not on the network here right now, so I will skip the demo. But you can prepare examples. The demo I had was just getting weather data off the internet. So I've got a map and I can just show weather at some selected spots. And of course, there are web services out there that you can access. The nice thing about object orientation, of course, is you can encapsulate. So there is some fairly complicated code in there that goes out to the net and pulls in the weather data and parses it and packages it into a nice object. That is all code that they can't write. It's too hard. But it's an object-oriented system. You write it, you give them the class, and all they need to know is how to do a method call to pull out the temperature in Berlin or wherever. So you can package it really nicely. You prepare the class with the hard stuff. You give them a nice, simple interface, and they can write programs that use real data, real time from the internet, and that starts being fun then. You can pull in a Twitter feed. You can pull in pictures from Flickr. There's a lot of stuff you can do, and of course there are many open data repositories and web services you can use. Sharing is very, very powerful. So one thing you can do in Greenfoot, once you have a program, like say this one, okay, let's take the Ant program. There's a share button here. Once that is done, let's reset that at first to some state, run that a little bit. Okay, so there's a share button. If we share this, there are 3 tabs here at the bottom. We can either create an executable jar file, so that is just a standalone version of this program. We can create a web page that includes an applet, but the interesting one is this one, the publish one. We can upload this program live to the internet. And I can here make an image for it by just manipulating the screenshot, write a description, and then just publish it on the internet. And now I had a bit trouble with my network connection before, so I will just check whether I actually can get a connection on now or not. Oh, I am live. Okay, my connection is actually working now. What it does is it exports the scenario to this web page. That's the Greenfoot website, and the Greenfoot website is a community website, and all the Greenfoot users can, with this one button click, if they have an account, push their projects out to the public onto the website. So you can think of the Greenfoot website as a kind of YouTube for Greenfoot games. So it's the same model. Anyone can look at it, and anyone can create an account. If you have an account, you can also publish content. So then you can upload your programs, you can leave comments, and so on. And then here, if we have something, this is now something really that I haven't seen. This is just something that someone has uploaded in the last few minutes. But then what happens here, if this actually runs, it's an applet, so it runs live in the web page. This one doesn't seem to be doing very much. Or maybe the connection is too slow to load my applet quickly, but you get the idea. You have seen applets. And then there is a comment trail. And here, for example, it says here 39 views. If kids upload their first example to that web page, and then an hour later they see, oh, 5 people have looked at it already, they get really, really excited. This is the equivalent of the picture on the fridge door, where in olden days in kindergarten, they came home to their parents and said, look, I made this, and their parents put it on the fridge. This is the look, I made this thing. They don't care so much about their parents, maybe it's more their friends, but sending the link to their peers and says, here's my game, that gets really exciting for them, and especially if they get feedback and comments on it. So, sharing is powerful. Sharing is powerful. So collaboration, showing it to others, that gets them going. And actually we get sometimes complaints. Well, I get computing teachers telling me that they now get complaints from the other teachers because the other teachers will say, the students now spend all their time on their programming. They don't study properly anymore. Because they actually, when they do programming projects and they put it up there and they get a few comments back, they often just keep going way past a school project or school assignment. It is very, very motivating. Another thing that's really motivating is to use gadgets. I've already shown you, Gamepads. Anything you can stick in there is good. There are things like these. It's called a Pico board or Scratch board. Comes from MIT. Was developed for another educational environment called Scratch. It's a sensor board that has light sensor, temperature sensor, and a slider and a few buttons, and you can then build some physical stuff around it. Or many of you will have seen this thing. It's a Kinect, a Microsoft product that they built for the Xbox originally. And we have an interface for the Kinect as well. So if I now open a project like this one, and I run it, I've got some balls falling around here. But what the Kinect does is a sensor that senses people in the image. So if I stand there, I can now interact with my game. So I can do things, I can catch the balls. And you get the idea. You can actually... That is actually where it really becomes fun. If you put that up on an open day in a school, all the kids are standing around it. That is, they just love to play with this. And then this is where it really becomes fun. The interface to the Kinect is reasonably simple. The Kinect does two things for you. One thing it can do is detect body outlines. That's what I used here, where it just detects the outline of a person, or actually multiple persons as well. And the other thing it does, I've used in another example, is it can do skeleton tracking. So instead of tracking the outline, it is tracking the coordinates of some of your body parts. So what you get there, if I stand here somewhere not too far away, is I'm getting the coordinates of the head, shoulders, knees, hands, and so on. And this is a paint program. So I can here with my right hand now paint. I have to look at the screen there to see myself. Left hand up is erase. So I can do that. If I put my right foot up, I'm changing my color. And if you look at the code for this, it is all in here somewhere. The code for this is here. So if you look at this, this is really the meat of the code. It is not a great deal of code. So what is going on there is, first line here, I'm getting the joint information for my right hand. I'm checking whether the right hand is the nearest joint, that is nearest to the screen. So I'm painting actually only if my right hand is forward. If my right hand is back, I'm not painting. So if my right hand is nearest to the screen, then fill over means, I'm painting a circle at the coordinates of my hand. That's the whole painting thing. That's it. Then the next if statement is just saying, if the y coordinate of my left hand is less than the y coordinate of my head, in other words, if my left hand is over my head, then I erase. And the last thing there says, if my right foot, again, I'm looking at the y coordinates, so I'm looking at the height, saying if my right foot is over my left knee, then I'm picking another color. So this is a level of complexity that within, a couple of months or so, the kids can actually write. So we have worked quite hard on creating an API that's really easy. Of course, all the cool stuff in the Kinect is in the drivers. That's not our code. The driver code is amazingly effective. And we've just put a layer on top to simplify the interface a bit for the kids. Last thing I want to show you, if you are still interested in doing something with Greenfoot, how you can get started in doing it. So there are a number of sources of material for you to use. One is the Greenfoot website, greenfoot.org. Well, you can, Google's your friend, you can always find it. I've shown you a little bit of it. It's a community website for the Greenfoot users, so people can publish their Greenfoot scenarios, and then there's often a comment trail. It is strangely positive, the tone on the... We've always, when we set this up, we thought we have to really police it, and then delete all the crap that will come in, because, we've got minors there, we have to look after it very carefully. It has never happened. The tone is really, for being the internet, surprisingly positive. There's lots of comments saying, this is great, but you could also do this. A lot of the time, ideas, how to improve things, and encouragement, and so on. There's also a discussion section separate from the scenarios, so just general discussion, and a lot of people ask for help, and a lot of people provide help. So there's a lot of, how do I do this? And someone says, well, look at this scenario over there, someone has done that a while ago. So a lot of support for the kids, and what that is actually doing for you, it's independent learning. So it enables you, if you run a computer club or if you go into school, if they are not all at the same point, and except for the very first minute, they never will be. You can just point them to something and say, if you have a problem, go here, find out. So that is the first source of information. There are also tutorials. Of course, there's the software download. It's a free and open source system, so the download is on there. There's documentation. There's a number of tutorials. One thing I want to point out especially is a series of video tutorials. So there's a sequence of short, about between 10 and 20 minutes video tutorials called The Joy of Code. Again, Google will point you to it if you want to look at it. So you do not have to have a whole set of materials prepared. You can go there, look at it yourself, or point the kids to it, and they can play around with it. The last thing I want to show you is another community site, but this is a community site not for the kids, but for the teachers or instructors. You know, people like you don't have to be a school teacher, you just have to be not a kid. The only people actually we want to keep out there is the pupils of the teachers, because there's a lot of teachers there talking about teaching and their problems, and well, there's also a lot of resources in there, including exams with solutions. So we want to keep school pupils out there. And the discussion, of course, is very different if you know that you're among peers and not public, because there are a lot of the situation with school teachers teaching computer science often is that they don't have a strong background in computer science. And so here they can actually openly say, I don't know what I'm doing, I'm teaching programming next week and I haven't got a clue, can anyone help me? And if it's public and if their pupils are reading this, they could never say that. So there's a gatekeeper thing here. This is not entirely open, but once you're in, there are a lot of teaching resources. There are a lot of project ideas and worksheets and so on, and help. There's a discussion section where you can talk to a lot of people and can get advice. So if you want to use Greenfoot, you're not on your own. You can go there and talk to other people. And even if it says educators, and it says it's a site for educators only, that does include people like you. It just means you should not be in 6th grade. Typically, when people apply here, we go into a dialogue with them and verify who they are and that they're not pupils. For an audience like this, we can actually set up access codes, and we have set up an access code. So if you use this access code for joining the green room, you will go straight in, and we can skip the step of having to verify who you are. This will be valid for a week from today. So if you're interested in finding out more and using the material, go to the green room, join, use this access code. And I have left about 10 minutes at the end for some questions, in case you have some questions. Otherwise, that is it from me. Okay, I have to see there are some. Okay, we start over there.
What's your experience with teaching to non-English speaking children?
Okay, the question is, what's the experience with teaching to non-English speaking students? Of course, at the age level we're looking at, so the target age for Greenfoot is about 14 years old upwards. And it varies a lot with age in different countries. So if you're talking to 18-year-olds in Denmark, you can speak English, right? But then, of course, if you're talking to 14-year-olds in France, there's just no chance in English. So you need translations. The Greenfoot interface itself has been translated into, I think, about 9 different languages. So you can switch the user interface language quite easily if that is one of the supported languages. If it isn't, if you want a language that isn't supported, you can make the translation. It's an open source system, and we ask for contributions. The labels that need to be translated, it's about 1 page of, A4 page of properties, pure text. It takes someone who's native in the language about an hour to do. It's not a great deal. So if you take the labels text file from Greenfoot and translate it to language and send it to us, you can do that in an afternoon and we will put it in. That's one half of the story. The other half of the answer is the actual material, teaching material, like tutorials and so on. And there are, in the green room, some resources have been translated. There is a little bit available in German. There are a few in French, not very much yet. But the green room has a sort of wiki resource model. So there is a collection of resources there that anyone can modify and improve. So if in your language there isn't enough there, we would appreciate you just to take something, translate it, and post it back. Okay, next question. Yep.
What about the code itself is English, right? Term 5, what would you do for French or other?
Yeah, that's a difficult question. So the question was, we're still talking about foreign language, and the question here is, what about the code itself? Because the Java code, move, turn, and so on, is in English. That is a very hard problem to overcome. Of course, the projects you write yourself, some of the methods come actually out of the particular scenario you're using. You could always do in a different language. But then some of them are Greenfoot API calls, and some of them, if you get a bit deeper in, will be Java library calls. And there you are always stuck with English. So even if you try to create your scenario in another language, you will end up with a half and half approach where some identifiers are local, some identifiers are English. There is no good solution to this, unfortunately. So you can get a certain way, but you can never completely solve it because some parts of Java will always be stuck in English. That's just one of the unfortunate situations of life for the non-English speakers. There's another question over there.
What are your plans for the future? Do you have any things?
Yeah, so the question is, what are our plans for the future? Do we have any plans? Yes, we have a lot of plans. First of all, we are certainly actively supporting the Greenfoot system. That includes further development of the software itself, and it includes development of material and support of the community. So we're creating the community websites and so on. And we've essentially, a few years ago, we've hit a problem of scale that, it's become big enough that we can't really interact with all the users anymore. That's when we started the community websites, where we try to get the community to engage with each other, and so that it doesn't all rely on ourselves. So a lot of the work over the last year has been in community support and community building and development of material. There's a whole textbook with it as well. So that's what we've worked on. On the software side, we are looking at the programming interaction. So we're looking at the moment at the programming task from an HCI perspective, because the biggest problem in writing in Greenfoot is the Java syntax. I've made experiments. I've used my daughter as a guinea pig, and I've used Greenfoot with her when she was 10, just to see how it works. And the story is, if I sit there one-on-one with her the whole time, you can just about do it. But she runs into stumbling blocks where she needs help. And the stumbling blocks, the most common one, almost exclusively, was Java syntax. She could deal with the concepts really easily. She actually understood what she had to do and what she wanted to do. But when she got her curly brackets out of whack, she just couldn't fix it. So there is the lower boundary for the user group of Greenfoot is imposed by the Java syntax. And that is about, if you've got bright kids, 12, 13-year-olds, if you've got sort of an average class, more like 14-year-olds, somewhere thereabouts, and you can't go lower. And so what we want to solve this by actually looking at the interactions, how you edit and work with and enter a program. For example, in Java, you can insert half a statement, right? You can have an if statement that has an open curly bracket but no closed one. Why? Why is it even possible to enter half a statement? I think we want to get away from character-based editing to statement-based editing, where you either have an if statement or you don't, but you don't, it just makes no sense to be able to write half a statement. And I think it's high time that we look at programming from an HCI perspective and look at, what's the interactions that we can really improve here. And I think we can do a lot better so that we can improve the interactions for kids and make it much more usable than it is now. That's one of the things we're working on right now. I'll just check my time. I've got 3 minutes, so I take one more question, and then I'll finish. Yeah.
Do you actually go to speak to teacher groups about what you're doing with this?
Yeah, so the question is, am I speaking to teacher groups about this? Yes, I'm doing a lot of teacher training workshops, and I'm in contact with various teacher associations in different countries, and we're going around. So we're talking a lot with teachers about this. And we're trying to find out what their problems really are, and what the effects are, and what the kids are doing with it. So we're trying to be reasonably close to the users. And the answer for that is actually different in different countries. But the one unifying theme is actually, at the moment, that most school teachers, so this is, aimed at secondary school range, most high school computing teachers are not trained well enough. In many countries, there are many teachers who have no computing background at all, who were dropped into the job sideways from being a PE teacher or, maths teacher or something like that. And that is one of the things, that was one of the biggest problems. There are some other problems. We try to see what we can do to address them. And that actually was what led us to create the Green Room, where we're trying to support them and give them material. We're actually seeing pretty much the teachers as much as our target group, user group that we work for, as the kids themselves.
A state-enforced curriculum.
Yeah, a state-enforced curriculum. And the details of the problems is different in different countries, but overall the big picture actually is scarily similar. Okay, my time is up. I will end here. Thank you for coming. Thanks very much.